Hello, everyone. Today, we will continue discussing together the remainder part of the diode circuits. So, just quick review for what we have discussed in the previous class. So, we discussed the clipper circuits. So, the meaning of clipper circuit again is if you have a certain input waveform with a certain value, you need to limit this volt at a certain voltage level. So, this is the meaning of clipping. And we discussed this circuit together. So, for instance, here in the circuit, you can see I would like to clamp or to make clipping for the volt output here at the volt level of VB of this battery volt. And actually, it's going to be the battery plus the turn on diode volt, which is the gamma. So I will add the battery volt with diode like that. If you would like to make the voltage level in the negative half cycle side, so you need to have the diode in the opposite direction. So you should reverse this diode. So by this way, you can make clipping for the volt. And we discussed this circuit together also. So this actually we have here in the two directions, in the positive half cycle and in the negative half cycle. So we have two reverse diodes like what you can see here, and two voltage sources in order to limit the volt at the levels we need. And also we discussed that instead of the battery, because the battery is one of the challenges we have in electrical circuit because of the lifetime. So instead of having batteries, we can instead replace these batteries by means of Zener diodes instead. So Zener diode can do the same function of the battery. So with the same polarity of VB1 here, plus here and minus here, we can replace it by anode and cathode of a Zener diode. So this is what we have discussed in the previous class, and we also solved one numerical example on this circuit. And here in this example, also we added one more thing, which is we added a resistance in series in the branch, which means now the voltage is not going to be clamped at the DC level, but the sinusoidal waveform itself will have a peak value shifted, as you can see here in this waveform. Okay, so this is what we have discussed in the previous class, and this is again the circuit that we could see in case of the replacing Zener diode, replacing the battery by means of Zener diode. So again, guys, so instead of the plus minus, you will have the cathode anode of the Zener diode here. So the Zener diode cathode is going to be in the positive polarity of the battery, and the anode is going to be in the negative side of the battery, as you can see. Why? It's opposite polarity compared to the plus minus of the V battery, because again, you know that the Zener is a reverse volt in the diode characteristic. The Zener volt is a reverse volt in the diode characteristic. So this is now the shape of the clipper circuit. So this is double clipper or double parallel based clipper circuit using Zener diodes, and this is called the voltage transfer characteristic. Another important circuit, guys, we use it for diode, or one of the important diode application circuits is clamping circuits. So the last one is called clipping circuit, and this is called the clamping circuit. What the meaning of clamping circuit? So let's understand together the meaning of a clamping circuit from this example here. So the clamping shifts the entire signal voltage by a DC level. So this is the concept of clamper. So clamper is going to shift the entire signal voltage by a certain DC level. For instance, here, the output volt we have in these circuits equals if you apply Kirchhoff voltage law here in this loop, so you will find that, let me write this here. So if you apply Kirchhoff voltage law here from this terminal to that terminal, you will find that V out equals, move in this direction, you will see the minus sign firstly, so minus VC, then plus the input supply, so plus the input. So we can say V out equals minus VC plus VI. Minus VC plus VI. As you know, guys, that in instantaneous waveforms, we represent the instantaneous by small letter like that, and the capital letter represent the average or RMS values. So now let's substitute in this relation. So VC plus Vn. So Vn is nothing but a sinusoidal supply. So it's V maximum sine omega t. And the capacitor, when you charge this capacitor, when the circuit starts working, so firstly the capacitor, the supply volts start from 0 like that, and it will increase. And according to the relation, when this diode is turned on, so this means in case of the ideal diode case, which means it's going to be short circuit, so VC plus V input will be 0, which means the capacitor volt will have the same voltage magnitude of the input. What the maximum value of the input supply? The maximum value of the input supply is the value of V max. So this means the end value of the capacitor is going to be V max as well. So the capacitor is going to charge until having VC equals minus or V max. So minus VC can be replaced by minus V max. So take V max common factor from here. So the relation would be V max times sine omega t minus 1. So this would be the shape of the output volt. Sine omega t minus 1. So at t equals 0, sine 0 equals 0. So the output would be minus V maximum. But for sure, because we have here transient, it's not steady state. Okay, so let's say at omega t equals, for instance, 90 degree. So at 90 degrees, so sine omega t is going to be 1. So 1 minus 1 equal 0. So the waveform will be 0, as you can see here. And if you represent at omega t equals, for instance, minus 270 degrees, so the value would be minus 1. So minus 270 degrees equals sine minus 270 degrees equals minus 1. So minus 1 again. So this is minus 2. So minus 2 V maximum. So the value would be minus 2 V maximum. So this is going to be the waveform we have here. So this means now, if we add the diode by this way, the output volt here, guys, is going to be added to an offset. Added to an offset or DC level. So this is the meaning of clamper circuit here. So it's make clamping or adding a DC level to the sinusoidal supply. So this is the capacitor volt that we discussed. So it will charge in the beginning until this instance, and after that it would be constant, or it will discharge according to the RC circuit of the circuit. But here we assume that we have ideal circuit, which means the resistor of the diode equals 0, which means now there is no discharge anymore in the capacitor. So this is the ideal case. Okay, so this is an ideal clamping circuit. Let's see another example here, guys. So if we have Vs the source volt, for instance, like the input that you have here. So this is the source volt V input. And you have this circuit, a capacitor here, and a diode and the battery. So diode and the battery, by this way, we know this circuit, actually we use this configuration to make clipping for our circuit, but here we added a capacitor in series. So let's see the configuration here. So in the beginning, again, the capacitor is going to charge until having the peak value, and then the output is going to be shifted by the same magnitude. So as you can see here, guys, instead of having the input sinusoidal like that, it will be shifted down by means of the capacitor volt. Okay, so this is the expected output of this waveform. So this is in case of having sinusoidal supply. In case of having, for instance, instead of sinusoidal supply, if you have let's say square wave, as you can see here, so it will be shifted down by the same magnitude here, which is the B, the battery. So by means of the volt we have here in series with this diode, we will shift the volt down like that. Okay, so this is the way, guys, how the volt is going to be shifted. So again, the peak value here is going to be the B or the battery volt. So it's shifted down as Vmax minus VB. Okay, and here as well. So it shifted down in order to be this Vmax minus VB. So the max is as you can see here. Okay, let's see a simulation for these clamping circuits. And in this simulation, guys, I'm gonna use here a different simulating tool, which is Matlab Simulink, and we are gonna move or make more discussion today in using Matlab. So the software here is Matlab, and the toolbox that will be used is called SimPower System. And I will show you today how to use this toolbox in order to implement any electrical circuit to simulate the electronic components. So here in this example, for instance, guys, we have here a simulation for the clamping circuit. So assume that we have V source equals 20 volt AC. So this is the value of the AC, and we have 60 hertz supply, and the battery volt here in our example equals 5 volt, and the capacitor, we have 100 microfarad capacitor, and we have a resistor of our load equals 10 kilo ohms. So these are the parameters we have in our circuit here. And in this circuit, we need to see some waveforms, like for instance, what's going to be the voltage output across this load. So we need to know what the V out, and also we are going to measure also here the current of this capacitor. So also the capacitor current will be measured here. So we connecting here a series ammeter to see the current, and we can detect the volt across the output volt here or the resistor here by means of voltmeter. But there is another way to detect the volt without having a physical multimeter here. I will show you how to do that in Matlab Simulink. So according to the waveform we have here, so what the peak value of the supply, so the peak value of the supply is 20. So this means the peak value here is going to be VB plus V gamma. So this is the maximum. The negative value is going to be minus V maximum minus V capacitor. So again, the capacitor here will charge with the peak value, which is going to be 20. And the battery volt equals 5 volt. So the expected output volt during turn on of this diode is going to be V diode plus, V gamma, which is the volt across this diode, plus the battery volt, so 5 plus V gamma. And when this diode is open circuit, so we expect to have V supply minus V capacitor, which is going to make a level shift for our waveform. For that, guys, that sinusoidal waveform, instead of having a peak of 20 volt, we have here now a peak of VB plus V gamma. So this is 5. V battery equals 5 plus the turn on volt. So the turn on volt, according to any diode semiconductor material, it can be starting, for instance, 0.6, 0.7, 0.8 volt. So here, in this case, we have 0.8 volts. So this is 5 plus 0.8 volt across the diode. So the peak value is 5.8, as you can see here. And the negative peak is going to be minus V max minus V capacitor. Okay, so this is going to be here minus 34 volts. So this is going to be the output volt. What about the capacitor volt itself? The capacitor volt is going to be charged until having this voltage magnitude here. Okay, according to this circuit, which is going to be V peak minus the battery volt. This is a zooming in for our circuit, for our waveform. So again, the peak value is 5.8 volt and the negative peak is minus 34.07. And the lower graph here is representing the cap volt. So this is the capacitor volt at steady state, Let's solve this example together, guys. So in this example here, we need to find the steady state output of the diode clamper circuit shown in this figure. So the input voltage Vi is assumed to be a sinusoidal signal whose DC level has been shifted with respect to a receiver ground. So we have a certain receiver ground, and we need to shift this AC signal by a DC value equals VB. So assume that V gamma equals 0. So the diode is going to be in the ideal case here, and the internal resistance of the diode itself is going to be 0. So we need to investigate the output of this waveform. So again, guys, this diode is going to be on for sure if the anode is greater than the cathode, which means the cathode has to be completely negative in order to allow this diode to be turned on. Okay, so in order to do that, again, so this is a simulation for our circuit. So this example, guys, we are gonna investigate the performance by means of simulation. So the supply volt again here is 20. The capacitor is 100 microfarad. And this is our diode, and we have a resistor here of 10K. So let's see together the performance we have here. So the input AC is the red one, and the green one here is representing the battery volt. So this is 5-volt battery here. And once the capacitor reach to steady state here at this interval, so the waveform will be completely shifted, as you can see. Okay, so this is gonna be the output volt in this case. So it's shifted by 5-volt. Okay. And also you can see here in the beginning, in the negative part is not gonna appear because we have the diode in parallel with the output, but in a steady state, it will be a bit different because it's after the capacitor charging, it will be relatively higher than the positive value. So you will see the waveform like that. Okay, so this is another case. Now, let's see the effect of changing the battery volt. So if we change the battery volt to be 10-volt instead of 5-volt, so what we can see here is the offset of the waveform has been changed. So it has been changed by means of 10-volt instead of 5-volt. So in the previous shape, this is the waveform in case of 5-volt. This is the waveform in case of 10-volt. And this is here the capacitor volt. Here, if the V battery equals 0, so the V battery will be removed from the circuit. So this is the expected output waveform for time being. Okay, so this is, guys, the wave shaping using clamping circuits. Now, I'd like to open with you the Matlab and see together how can we use Matlab Simulink and SimPower system in order to make a complete simulation for the diode circuits. Okay, guys, now the Matlab is opened. So let's see together how to create a Simulink model. So I'll start from scratch with you guys. So when you open the Matlab, the main window will appear to you like that. So in order to create a new project, so go to New, and then select from New here, Simulink model. So this is gonna open a new Simulink model for you. So I will show you how to reach out to the elements, how to reach out to the sources, how to reach out to the measurements, and how also, if you would like to make a certain mathematical function, how can you do that in Matlab Simulink. So this is another model is open for the time being. So it takes some time to initialize and opening the MATLAB file. So as you can see, guys, it's opening here a new window. And in this new window, I will create a new Planck model. So create model here. So this will open a new project, as you can see here. First thing is we need to see where is the library that we are going to use. So Matlab, guys, has a big library. So we will see together which toolbox we will use in order to implement our circuit today. One of the well-known toolboxes is called SimPower System toolbox. So in the SimPower System, we will have some electronics and power electronic components. We have some other power elements. So we will see together how to use it together. So here we have our library. Under SimScape, we need to find the toolbox we need. So firstly, I'm going to double click here on SimScape. By the way, how to reach the SimPower system, it may be different from a MATLAB version to another version. So this is here for 2024 version. I wish this is the same version you have on your computers. So go to electrical. You will find specialized power system. And under specialized power system, you will find some libraries we are going to use. So this block is very important, guys. In order to have any SimPower system toolbox, you have to drag and drop this block. It's called Power GUI, Graphical User Interface. So we have to drag and drop this in our model in order to allow us to simulate this toolbox. And then here you can find every elements you will need. So for instance, you have control blocks, you have electrical machines, so all types of electrical machines you can imagine, you can find it here, all motors, generators. You can find any type of passive elements, resistance, inductance, capacitance, transformer, surge arrestors, and so on. You can find power electronic elements, and this is a part we will use today. So today we will make, for instance, an example for a full wave rectifier and see the performance using Matlab Simulink. So we expect to use diodes. So one of the elements here is diode. So I'm going to drag and drop this diode like that. So this is diode, but we have something else here. So I will describe this now, what the meaning of this element here. Okay, and we have other elements. We will use it after that, after a few classes. So in the next class, we will start in a new type of semiconductor switch. It's called the MOSFET. So you will find the MOSFET here as well, and we will use it also, and so on. So these are the different power electronics or electronic component we have here in this toolbox. Also, we have sensors and measurements. So we will use some of these measurements, at least the voltage and current measurements. And also we have the sources. So in the sources here, all type of sources you can imagine, you can find it here. So in our example now, we are going to make rectifier. So we will need AC source. So I will need an AC voltage source. So I'm going to drag and drop here AC voltage source. And we will need passive elements to work as a load. So I'm going to select here a passive element, like for simplicity, let's select resistor. So you cannot find resistor alone, but we have what's called series RLC branch. So I'm going to drag and drop this series RLC branch here. And let's see how to make a full wave rectifier. So you know guys, all the full wave rectifier consists of 4 diodes. So this is our diode. You can rotate the element. So I will press Ctrl R in order to rotate the element. I will rotate it in this direction. If you double click on the diode here, you will see the internal properties we have for this diode. So for instance, the internal resistance is 1 milliohm. The forward volt is 0.8 volt. And the initial current is set to 0. And another important thing here, guys, is the snubber circuit. So what the snubber circuit? Actually, snubber circuit is mainly used for relatively high power applications in order to allow filtering the noise on any semiconductor material. So for the time being, we don't need these kind of snubber circuits. So the snubber circuit consists of R and C in series. In order to remove this snubber circuit, we need to have infinite resistance. So infinite resistance means it's open circuit. So instead of 500 ohms here, for instance, I'm gonna type INF. So INF means infinity. So once I type INF and press OK, so this resistance will be removed from the element. As you can see, the resistance in parallel with the diode has been removed, or the snubber circuit has been removed. Another thing, guys, here we have show measurement port. So show measurement port, this letter M here. So this port can show us the different signals on this diode. I'm gonna keep it for the time being to see the performance of this diode. After that, if you would like to remove it from the shape, so uncheck this box. So it's gonna be without this M. I will show you firstly. Now I unchecked. So as you can see here, the element, we don't have anymore the M port. Okay, let's have it like that for the time being, and later on we will show the port again to see the elements, sorry, to see the waveforms of this diode. And you can rename this. Let's say I'm gonna say this is D1 now. For a full wave rectifier, I will need 4 diodes. So simply I can make copy and paste. So in order to copy, press Ctrl C, and then you can press Ctrl V. So this is a way to make a copy. And to connect between the elements, just connect your mouse. As you can see, guys, when I paste the other elements, the designation has been changed automatically. So it's make counting automatically. So the second element is D2. Another way to make copy and paste, just use your right click mouse. So right click, hold your right click and move it here. So it's gonna make another copy. So this is D3 and D4, as you can see. Connect between the elements again. So this is gonna be the positive terminal, and this is a negative terminal of your rectifier. And now I can connect here the positive terminal of the AC to the midpoint, and the negative volt of the AC here to the other midpoint. And we need to connect our load now. Now, this is our load. I'm gonna make it here, for instance, R load. And I would like to change the orientation. So Control R, this will change the orientation, as you can see. And I will connect this to the output of our rectifier. Now, if you double click on the RLC branch, it will open this window, and you can select now between the different elements. So you have the many options, actually. You have the different options. You can select only resistance, only inductance, or capacitance. You can select R and L together in series. You can select R and C. You can select L and C. You can select open circuit, which means nothing. So now let's select just a resistance here for the simplicity, and type the resistance value. So I will add 1 kilo ohm, so 1,000. And here in the measurement, you can select anything you need. You can measure the voltage of this branch, the current of this branch or both voltage and current. So let me select both current and volt of this branch. So I will select this option, press OK. So this is now our circuit. For the AC source, if you double click here on the AC source, this window will pop up. So we have now, for instance, the supply volt is peak of 100. You know, guys, the supply we have in domestic loads is 110 or 115 RMS value. So the peak value is going to be 150 something, maybe 154, 155, something like that. Or instead, you can say 115 times skirt, which means square root of 2. So it will multiply automatically. So here it gives you 162 in case of 115 RMS. In case of 110, I believe it would be 150 something. So 110, yeah, 110 is 155. So this is the domestic loads domestic supplies we have here in our homes. Frequency is in hertz, so it's 60 hertz. Sampling time, 0 means it's going to be the default of your simulation. So let's keep it 0 for the time being, and we will discuss what the meaning of sampling time soon. And then here for the measurements, since this is a supply volt, you have only option to measure the volt of this source. So I'm going to select also V in order to see the output, the waveform of the supply volt. And I will press now OK. And this is our simulation. Also, you can change the name, as you can see here. I will say this is VS. So this is now our circuit, guys. And for sure, you can drag and drop the name anywhere. In order to zoom in, you can just press space button on your keyboard. So this is space button. I will press on it now. Move this like that. So this is now the shape we have in our model. Now, I said I need to measure the output volt and current, the supply volt, and I selected already to measure these values. How can I grab the measurements? So we have what's called multimeter. So how to get it? If you go to the library here in the left-hand side again, and go to the measurements, so here in sensor and measurements, you will find, scroll down here, you will find multimeter. So select the multimeter and drag it in your model. So can you see here we have now 0. 0 means we have 0 signals now to see. If you double click now on the multimeter, it will open a new window and you can find the different signals you have selected, you have initiated for measurements. So as we mentioned, we have R load. So this is our R load. So we have UB, which means the potential or the voltage of this R load. Then you have U source VS. So this means the supply volt of the element VS. And then IB of the branch current of the R load. So let's say I will select firstly the output volt of the load. I will select. So when I selected, it came here to the right-hand side window. I will select next to the current. So this is the current. So select again. So this is going to be the current comes after that. And lastly, I will select the input supply volt. By the way, if you press here, you can move up and down. It's up to you. For instance, I would like to move VS to the first of the list. So I'm going to make it up. So up for one time. Okay. Again, press here and up for one more time. So it came to the beginning of our list. So this is going to be now the number of signals that I will measure. So before of opening this block, it was 0. Now I'm expecting I will have 3 signals to measure. So once I press OK, so I find here the number turns to 3, which is the number of measurement signals that we will record. Now, where should I see these signals, we need to get an oscilloscope. Where can find oscilloscope? Actually, scope is not in the same power system. This is in the Simulink library. So if you go to the Simulink library and go to Sinks, you will find scope. So this is here, the scope. So drag the scope here in your model. And if you now connect this, so this should record the 3 signals we have. Now, we made all the connections. We made most of the settings. However, one of the important things is the solver. If you go here, guys, on the right bottom, you will find auto variable step discrete. So it's auto now. If you go to the setting, you can select your solver. So for the same power system, guys, we have some different solvers. If you go to here, you will find we have variable step and we have fixed step. Okay, so we do prefer to have a fixed step for the digital-based elements, but variable step is preferred in power systems. So let's keep it variable. And here it will make like auto selection, or you can select a certain solver. So the solver that we do prefer in case of power and electronic components is ODE 23S or 23T. So let's select ODE 23T. ODE is stands for the ordinary differential equation. So this is the technique of solving the differential equation. So now I selected the solver. Regarding the start time is 0. The stop time, let's select the stop time just 0.1 second. And press apply and OK. I think now everything is ready to run this simulation. Let's run the model together, guys. So go to this play button and press run. So firstly, the compilation is started. So it's finished the compiling now. And now the simulation is finished. In order to see the recorded waveform, so we need to open now this scope. Double click on the oscilloscope, guys, to see the signals we have.